So after talking about significant figures, we can talk about accuracy and precision. And this will come up in lab. Accuracy and precision are not the same thing. So accuracy refers to how close the measured value is to the actual value. So one analogy that's sometimes used is throwing darts or shooting arrows. And you want to get the bullseye, right? And so accuracy is hitting the bullseye, hitting the center. If you're not hitting the center, if you're not close to the correct answer, it's not accurate. Precision happens when you have more than one measurement of the same thing, and they can either cluster together and very much agree with each other, or they could be all over the place. So precision might be, I'm shooting arrows, and I'm just like always off, but I'm off really consistently, right? And so all the arrows go over there. They're really close together. This is precise. It's not accurate, though. So you can have one without the other. You'd want to have both of them. But precision is how close your answers are to each other. And we can measure that with standard deviation. We'll learn that next week. Accuracy, how close is my result or my average result to the true result, and we can measure that with percent error. Here's a little example. 3 students taking a lead block that weighs 10 grams, and they're each weighing it 4 times and seeing what they come up with. The table, hard to look at, doesn't really tell us very much. This is why scientists use graphs. And so sometimes it takes a little bit to understand what the graphs are doing, but once you do, then you can just get a lot more information out of it quickly. So if we look at these 3 graphs, what do you notice that's different about them? What's different about this one? Lots of different heights, right? So this is showing the measurement of mass each time the student did it, and the numbers are very different from each other. So the numbers are not agreeing. That's not precise. That's imprecise. Whereas these guys, they're all really close, and these guys are all really close. So both of these we would call precise. When you have multiple measurements, you can use the average. So the blue line is telling us the average. The dotted line is telling us the average. The blue line is the true value. So here, the actual average is above the true mass, not accurate. Here, the average is below the true mass, not accurate. And here, it's very close to the true mass. So this data is accurate and precise. And that's what we'd like to have. It's not always possible. So we see 2 basic kinds of error. There's random error and systematic error. Random error is random. So you're going to have some random error every time you take a measurement. It might mean that your measurement is too high or it is too low. It has an equal chance of being high or low. Because it's random, if we make that measurement several times and average it, the errors should cancel out. And that's why we measure things usually 3 or 4 times and take an average, because we can get rid of that random error and make things more accurate. The systemic error is one that is going to go in one direction or the other. It's going to be too high or too low. This can be a result of poor technique. You just really don't know how to read a burette and you're just looking at the wrong thing, right? Or it can be that there's something wrong with the instrument. If your balance is messed up, it could be reading things too high. right, or too low. But when students come up with errors in the lab, they often say, well, it was the balance. Probably not. Those balances are really accurate and we take good care of them, so it's probably not the balance. But a balance could cause error. If you're using, if you're using a meter stick to measure something and the end is broken off, and somehow you don't notice that, and you're using like 6 as 0, that's going to cause all your measurements to be wrong, right? It's going to give you systematic error. Averaging doesn't help with that.